All right, so we've talked a good bit about heat, and we've talked about different types of reactions. We've talked about enthalpy now, and what I want to get into is a little bit of what is the sort of question that you can expect from this. So, first and foremost, enthalpy is an extensive property. We've previously talked about extensive properties, and in this chapter we talked about an extensive property. We talked about heat was an extensive property. I gave the example of, if you had a glass filled with gasoline and you lit it on fire, compared it to a 55-gallon drum filled with gasoline and you lit it on fire. One of them is going to produce more heat. So enthalpy is an extensive property. It's dependent on the amount of that material. And we see that in this type of reaction right here, which go ahead for a little bit of a review. When we have a hydrocarbon, that's an R, and a hydrocarbon plus O2 plus oxygen is going to produce carbon dioxide and water. What type of reaction is this? This is a combustion reaction. So a combustion reaction. What this shows is that we have a delta H of negative 802 kilojoules. Okay, so what that tells us, if we have 1 mole of CH4 react with 2 moles of O2, we're going to produce 1 mole of CO2 and 2 moles of H2O, but we're also going to produce negative 802 kilojoules. Okay, now let's think back. Is this a endothermic or an exothermic reaction? So an endothermic reaction is one that is going to be cold and it's going to have a positive delta H, whereas an exothermic is going to have a negative delta H value. Okay, so this is an example of an exothermic reaction. I always like to go ahead and think back to this. What type of reaction is this right here? This particular example is a hydrocarbon plus O2. We are going to basically combust it to make CO2 and H2O. It has a negative delta H value. That's an exothermic reaction. I like to think about this in the context of as an example, like a vehicle or something, an internal combustion engine. You're going to use gasoline and you're going to provide a little bit of a spark and you're going to produce a small or a massive amount of energy. And so anyway, just simply as an example to kind of jog your memory on these sorts of things. So this is an exothermic reaction, negative delta H value. But what this is actually getting at is enthalpy as an extensive property. So if we had 2 moles of CH4, we would need 4 moles of O2 to react. We'd produce 2 moles of CO2, 4 moles of H2O. So what would you imagine that your delta H is? Well, we've got 2 times as much of all of our material, so you should expect to see a delta H that total is negative 1604, so 2 times as much. So another thing to consider with these sorts of reactions is the enthalpy change for a reaction is equal in magnitude but opposite in sign to the enthalpy change for the reverse reaction. So what we just showed was if you react CH4 and O2, you're going to produce CO2 plus H2O, and you're going to have a release of heat. So the idea here is that if you look at the opposite reaction, so this is basically what I just wrote out, if you look at the opposite reaction, and that reaction would be if you tried to react CO2 and 2 moles of H2O in order to produce CH4 and O2, well, you would have to input that same amount of energy. So the delta H for this is going to be positive 802 kilojoules. And I'm going to press next, and lo and behold, the number is going to appear. Yeah, that's what I meant to do. So delta H, let me erase all that so it's a little bit more clear. Well, it's going to be the equal and opposite value. So this same reaction, or this opposite reaction, is going to require the opposite amount of energy to be input. Okay, now information in a chemical reaction can be used to predict amounts of heat given off or absorbed by a specific reaction. So this particular reaction right here, calculate the quantity of heat produced when 2.5 grams of NH4NO3 decomposes at constant pressure. So this shows us our reaction. Ammonium nitrate reacts to produce N2O and 2 moles of H2O. Okay, so this is just another jog your memory. This is a decomposition reaction. And this decomposition reaction produces a release of 37 kilojoules of heat. Well, that's when you have 1 mole. Okay, so what I want you to think about here is if you have 2.5 grams. So ultimately, this is going to be a factor, this is going to be an example where you're going to take grams to moles to kilojoules. But you actually kind of already have this. So this effectively shows you that the decomposition of 1 mole of NH4NO3 is going to release negative 37 kilojoules per 1 mole of NH4NO3. Okay, so if you look right here, I've magically been able to get the molar mass of ammonium nitrate to pop up on the screen. And so what we need to do is we need to go ahead and look at this equation and put it in dimensional analysis. So 2.50 grams of NH4NO3, that's the molar mass of ammonium nitrate. So if you have 80 grams of it, NH4NO3, you have 1 mole of NH4NO3. So if you look at that, we have considerably less than 1 mole. We only have 2.5 grams, and 1 mole is 80 grams. So then if we complete this dimensional analysis, that's where we're going to bring in this enthalpy factor. So negative 37 kilojoules per 1 mole. So we want to plug that in, negative 37. And we don't have a problem using that negative there just because of the fact that, well, we're going to be doing multiplication, not any sort of addition or anything like that. Negative 37 kilojoules per 1 mole of NH4NO3. I related these things back. So whenever I look at what are the things that I'm going to eliminate, well, my grams of NH4NO3, my grams of NH4NO3, my moles of NH4NO3, my moles of NH4NO3 are going to all be eliminated. Now, whenever I plug all of this in, which I'm going to, when I plug all of that in, I get 2.50 times negative 37.0 kilojoules divided by 80, and that's going to give me 1.16 kilojoules. One important factor is this is negative. This is still going to be releasing energy, but it's going to be releasing a very small amount of energy because I have considerably less than 1 mole. All right, well, I hope this was helpful. Thank you very much.